So we have learned that an integral gives us the visual of an area between the function and the x-axis. All right, so for example, let's say we have an f of x function that kind of looks like this. And that f of x function intersects the x-axis at point A and point B. And so back in chapter 6, we learned that we could write an integral. We could use integral notation to represent the area that was, we say, bounded between the function itself and the x-axis. And so we write that area like this. The area on the interval from A to B, parentheses, that was a key part that you got docked points for if you didn't have that, f of x, and then dx indicated that we're going on the x-axis as our boundary. All right, so that means we could also take different functions. Let's take something that looks like this. And if we wanted to find the area that was bounded on the y-axis for that, okay, so we'd have a horizontal line that went straight across, that we could write an integral expressing that, except we would need to be in y terms. So along the y-axis, perhaps we're going along the interval from C to D, and we would write now that area as the integral with bounds from C to D, parentheses, and then this would be written f of y, because we're now in y terms, dy, to show that we're using the y-axis as our other boundary. All right, could you overlap the two and then find out the area between both of them at the same time? So let's try drawing that and see how that is going to look. Okay, so let's draw this original function. And then let's draw the exponential that comes through. So if you're not using the x-axis or the y-axis as your exact boundary, but you want to use two functions as the boundary between the two, and so then we're finding the area this way. So how do we write that? Well, our boundaries aren't going to be on any particular axis. Our boundaries are going to be at the coordinates of the intersection points. So we would need to identify what these intersection points were, here and here. So let's call this one x1, comma, y1. And then let's call this one x2, comma, y2. Now you can express this area in two different ways. You can either use the x values or you can use the y values. So let me show you how you would write that. All right, our area, if we decided to use the x values, then we would say we're going from x1 to x2, parentheses, and then you list the upper function minus the lower function. And so we list f of x, which is the higher of the two functions. It's always above. And then we subtract from that, and we'll call that lower function, we'll say that it was g of x. Now we still are going to use dx as our differential. And really all that does is explain that we are doing x terms, which means we are going horizontally from left to right. Okay, so we're going to use those. Sometimes that integral doesn't work out so well, like it's just not an easy integral to do. And so you could try it in y bounds as well. And so you could say, well, or I could try going from y1 to y2. And I could try f of y minus g of y dy. In other words, we want to get everything in terms of y. One of those or the other is going to be an easier function, an easier one to work out. We're going to focus on the y's tomorrow, or Friday, I mean. We're only going to focus on doing the x values today. Yeah.
How do you determine which function?
Okay, so yeah, I'm going to teach you that on Friday when we talk about that, because in this case, the way this one is done, it passes the vertical line test. And anyway, yeah, I'll explain it on Friday. We're just going to only do x terms today. All right. Now, another situation might be where this picture is extended a little bit. So let's say that you have a function that does this, but then instead of crossing the x-axis, maybe it turns back around again. Okay, so that's our f of x. Well, let's draw the g of x that we had before that comes through. Okay. Now our exponential in this case crosses this graph. Well, how many points of intersection are there? There are 3 points of intersection. Okay, so that there's a point of intersection that forms this first section. Okay, and so we'll label those intersection points the same as we did before. Oops. So x1, y1, and then this one here would be x2, y2. But then for the next section, the roles of the function reverse, and one dips below. The f of x dips below the other one. And so my function is, my area is like this. And now we have a third intersection point, x3, y3. And this is the g of x function, the lower one. All right, so then how would you write the area expressed between those boundaries? Well, the first section of area is written the same as what we have done it before. When we go from x1 to x2, parentheses, for that section, the upper boundary is formed by the f of x function minus the value of the lower boundary, which is formed by the g of x function. And we're working from left to right. Then we add to that a second integral, which is going to represent the second section of area. And so that would be from x2 to x3. But in that second section, the roles are reversed. And the exponential, the g function, is the one that's considered the top. And so g of x is first, minus, and then the f of x is the lower function, but I'm still working from left to right. So for every section of intersection points, you'll set up a new integral to find the value of the area for that region. If you're not sure which one should come first, I kind of think of the top to bottom approach. If I were to drop an arrow from the top to the bottom, my arrow in that section is going to intersect or cross through the f of x function before it would cross through the g of x function. But in the second section, if I dropped an arrow and I just let it drop and it came through, it would cross through the g of x function before the f of x function. So those two things get reversed. All right, sometimes you're working with like sine and cosine functions. So let's think about those. I'm not going to draw an x-axis, but let me just draw a sine graph. And this is the origin. It's 0, 0. And then maybe we have next to it a cosine graph. Well, cosine starts at 0, 1. And then cosine kind of runs alongside. All right, there's the cosine graph. Find the area between them. Okay, so if we're drawing the area, we want to find this area connected to that area, connected to this next area, and on and on and on and on. So there are infinitely many intersection points of sine and cosine. Okay, just remember, sine of x is the one I've drawn in white because it starts at 0, 0. And cosine of x is the one I've drawn in blue because it starts at 0, 1. So let's find the shaded area up to the end of that intersection spot right now. So this will be our first official example. And what we would need to know, again, like this is without a calculator, we would need to find the intersection points every time sine and cosine cross each other. And so let's think about that. When is the first time that sine and cosine are equal to each other? Okay, at pi fourths. So this value right here is pi fourths. And what value do they both share right there? Rad 2 over 2. The next time sine and cosine are equal to each other, okay, down here, is when? When are sine and cosine the same? 3 pi fourths, they're different. That's in quadrant 2. And in quadrant 2 at 3 pi fourths, the cosine is negative, but the sine is positive. At 5 pi fourths, they are the same, and both of them are negative rad 2 over 2. So that would be the next intersection point. And then the last one we're going to consider is back around the unit circle again. Okay, how many pi fourths is that? 9. Okay, got to know your unit circle. Yeah, it's 9/4 pi. Okay. 9/4 pi. And then we're back to both of them being positive, rad 2 over 2. Okay, so then we set up an integral that would represent those 3 distinct sections of area. And so the area would be as follows. The first section starts at an x value of 0, and we're going left to right, and ends at pi fourths. And in that first section, the smallest piece of area altogether, which function is forming the upper boundary? Cosine is, because it is the one that's starting at 0, 1. And so cosine would come first, minus sine of x would come second, dx to show that I'm working left to right. Then I'm going to add to that the next section of area. And I can't really use symmetry here because these shapes are very different shapes. But my second section of area will start at pi fourths and end at the intersection point of 5 pi fourths. And for that section of area, the sine is now the larger function. And so I'd have sine of x minus cosine of x, dx still working left to right. And the largest section of all would be the final section. And that's going from 5/4 pi and ending at 9/4 pi. Bless you. And in that section, cosine again has taken over as the higher function. And so then you'll work through each antiderivative and each set of bounds and add up the values to have your final amount. So I'm actually, I think, going to work this way. Going to kind of do them independently from each other and then add them up. So I'm going to call this area sub 1, and I'll call this section area sub 2, and I'll call this last one area sub 3, and then I'll eventually just add them up so I can find the total. That's easier for me to kind of work across. All right, so I'm going to work through my antiderivative. Antiderivative cosine is negative sine, minus the antiderivative of sine is cosine, plus c, going from 0 to pi fourths. Area number 2 would be the antiderivative of sine. I just corrected a negative sign, so make sure you do that in your notes. Okay, antiderivative sine is negative cosine minus sine plus c, going from this time pi fourths to 5 pi fourths. And then area 3 would be the antiderivative again, so sine of x plus c, going from 5/4 to 9 pi fourths. So this is no different than the antiderivatives you were doing in the past. All right, I'm just going to keep working sideways as I plug in my bounds here. So I'm looking at the sine of pi fourths plus the cosine of pi fourths plus c, which will cancel out, minus the sine of 0 minus the cosine of 0. Now don't make the foolish mistake of just thinking that the cosine of 0 and the sine of 0 both cancel out. The sine of 0 for sure does, that is 0, but the cosine of 0 is not. And so for this one we'll end up with rad 2 over 2 plus rad 2 over 2 minus 1, which when you add rad 2 over 2 to itself, you end up with rad 2 minus 1. All right, so that's the value of the first section of area. It's the smallest one. If you were looking for a decimal value for that, rad 2 is 1.414, so subtracting 1, it's about 0.414. So, but it's the smallest area section. Okay, so then the next one, we'll have the negative cosine of 5/4 pi minus the sine of 5/4 pi, and then minus the negative, so plus the cosine of 5/4, and plus the sine of 5/4. So I've got negative cosine of 5/4, which is also negative. So I end up with positive rad 2 over 2. And then positive rad 2 over 2 again. And again. And again. And so that gives me altogether 2 rad 2. So that's the second chunk of area. And then for the last one, we'll plug in 9/4 and 5/4. So we have the sine of 9/4 plus the cosine of 9/4 minus the sine of 5/4 minus the cosine of 5/4. All right, so the last one, we end up with rad 2 over 2 plus rad 2 over 2 minus a negative rad 2 over 2. All right, so I end up with 2 rad 2 again, which might be a little bit surprising to you. That just goes to show that my graph is not to scale, but those two area regions, area 2 and area 3, are actually the same value. And so now we want the total. We want to be able to add up the beginning second area 1, area 2, area 3, and area 4. So rad 2 minus 1 plus 2 rad 2 plus another 2 rad 2. So your total, when you add that up, remember adding radicals is like adding like terms. And so the total area, there are 5 rad 2's altogether, minus 1. And so that's the area of all 3 of those sections put together. Okay, any questions on that part? So you can see how your unit circle comes in handy. All right, I want to do 2 more examples with you, one without a calculator again, and then one with a calculator. So here is example number 2. In example number 1, you had to, be decent at your trig. Here you've got to be decent at your algebra. All right, so find the area between the following 2 curves. Y equals negative x squared plus 4x plus 2. And also between y equals x squared minus 3x plus 2. Okay, for this one, you don't have to be perfect at graphing, but you should understand what shapes you're looking at. And let me call this one y1, and let me call that one y2. y1 is a parabola. It happens to be the shape of a parabola that's upside down. You do not have to graph a perfect parabola on an axis, but you should draw a parabola that's upside down. Okay, it doesn't have to be on the axis anywhere, but you should have a general idea. Oh, that's an upside down parabola. What's the easiest point on that parabola to find? Yeah, sure, plug 0 in. What do you get? Okay, you get 0, 2. Now that's not the vertex of the parabola, that's just the y-intercept of the parabola. Okay, so that doesn't necessarily mean that that is the top, it's not the max. It happens to be about right here, where you've got 0, 2. All right, the other parabola is also, the graph is also a parabola, but it's right side up. And what's the easiest point to find on that? It's also 0, 2. Interesting. Okay, but it's right side up. That graph ends up looking like this. So our job is to find the area between them, which means we need to find, now clearly we know what one of the intersection points is, 0, 2, but we need to find this other intersection point over here. And so this is where I said you got to be, your algebra, you need to know how algebraically to find those two. We know that they both share 0, 2, but where's the other intersection point? Okay, how do I find that? Sure, set them equal to each other. So you got to do a little algebra before you can do some calculus. So negative x squared plus 4x plus 2. And you're going to set that equal to x squared minus 3x plus 2. And you're going to solve. You want to set that equal to 0. That's always a good algebraic technique. So I'm going to add x squared to both sides. I'm also going to subtract 4x. And I'm going to subtract 2. So I cleared one side out completely, and I end up with 2x squared minus 7x. And then the plus 2 and minus 2 cancel out. So I solve that with factoring. They have x in common, which leaves me with 2x minus 7 as the other factor. And so x equals 0. And x also equals 7 over 2. And those are the two intersection points. We already had the 0, but now we know that this other intersection point here is now 7 over 2. You don't have to find the y value of the intersection point unless you were integrating in terms of y. So this is 7 over 2, comma, and then it's the other y coordinate. It doesn't matter what that y coordinate is because we're only going left to right. We're not going up and down. So now we're ready to, our algebra is done. We're ready to do our calculus, which is setting up an integral. So the integral will go from the bounds of 0 to 7 over 2, parentheses. The upper equation is the one that was formed by the upside down parabola. So that's negative x squared plus 4x plus 2 minus the value of the lower, or the equation for the lower parabola. When you subtract, make sure you change all the signs. So x squared plus 3x minus 2. And then we say dx to indicate that we're going left to right. So your algebra is done, and now you're ready for the calculus part of the problem. And so your equation simplifies by combining like terms. We get negative 2x squared plus 7x. And then we're left with dx. So we're ready to do the antiderivative. Antiderivative of negative 2x squared is negative 2/3 x cubed. And the antiderivative of 7x squared, or 7x, is 7/2 x squared plus c, going from 0 to 7 over 2. So we'll have negative 2/3 times 7/2 cubed plus 7/2 times 7/2 squared plus c, and then minus all the zeros. All right, so the c's cancel out, and the 0 terms are negligible. You might be a little intimidated at cubing and working this out, but it's really not that bad if you notice that this is actually just like terms. This is negative 2/3 times 7/2 cubed. The second part, if I combined the 7/2 as the coefficient, and the 7/2 squared, I end up with 7/2 cubed again. So I have -2/3 times 7/2 cubed plus 7/2 cubed. In other words, my GCF is 7/2 cubed, leaving me with -2/3 plus 1, or 7/2 cubed times 1/3. Okay, 7 cubed is 343. 2 cubed is 8 times 1/3. So it's 343 over 24, which is not reducible. Okay, any questions on that? All right, for the last example, you'll need to be in radian mode and you'll need your calculator. All right, our final example is this. Within the bounds of 0 to 2 pi as a closed interval, find the area bounded by the functions y equals cos x and y equals e to the negative x. So before we use our calculator to graph it, we should visualize what we're looking at first. Okay, cosine of x starts at 0, 1, and the graph of cosine of x looks like that and ends at 2 pi, comma, 1. Okay, that's the graph of cosine. The graph of e to the x. Right, e to the x comes down through quadrant 2. It intersects also at 0, 1. Okay, then comes down, but it stays above the x-axis. And so our area is going to be this little tiny sliver here, and I'll need to find the intersection point, followed by this large part, and even though it dips down below the x-axis, you don't have to worry about that. And then it comes up to another intersection point. And then finally, I'm cutting it off at 2 pi, and so I'll be looking at the area bounded here. All right, so now we're going to use our calculators to find the value, to calculate the value of those intersection points. You want to write that A equals 1.292695,719. And just draw an arrow to right there. Okay, just say A is going to be equal to that. And it tells the reader that you stored it. Use it in your A value. Okay, now we want to do B. So B is 4.7219, 92759. All right. On paper somewhere, you have to record what the letters are. When you write your integral, to set up the different regions of area, so area 1, area 2, and area 3, you can use the letters instead of the really long values, as long as you've written it somewhere in your work. So your first area would go from 0 and then just use a. And in this case, the cosine was the upper function and e to the negative x was the lower function. For area 2, you would use the bounds a to b. So it's totally legit to use letters as your bounds as long as you've written down what the letters are somewhere else. For this second section, for area 2, the exponential is now the upper of the functions, and so it would lead. What do you think would happen if you got the order of the functions wrong? You get a negative answer. You can't have negative area, okay? So between two curves, you can't have negative area. So that should be a big clue if you get a negative number. And then area 3 would go from b to 2 pi. And then that's back to having cosine of x minus e to the negative x dx. So as long as you write the integrals down, that is the only work you have to show. If this is a calculator active question, you have to write down what the alphas are that you're using, write an integral in the right form with the parentheses and the dx and all of that, but you don't have to show any work. You don't have to show any antiderivatives. You don't have to show anything. 3.456 to the nearest third decimal place as your value.